Morning, everyone. Thank you, Tim, for the introduction, and thanks to Mike for inviting me to participate in this conference. It's an honor to be here and to hopefully entertain you and educate you a little bit about what we found in response to Hurricane Sandy, and also to talk a little bit about how we actually could have, in some ways, predicted the response of Fire Island, Barrier Island to Sandy based on what we know about the long-term geologic framework and Barrier Island evolution. I'm just going to move right along, hopefully. Oh, I did want to, before I go on, I wanted to point out this is a huge effort by both colleagues at the other offices of the USGS and the National Park Service. These are people who really directly contributed to the effort, but there's other folks like Mike Bilecki, who's here today, and Katie Kerr, who helped immensely in the field, and of course Chris Solar, the superintendent of the park, that were just behind the scenes invaluable to us for a lot of this work. So today, the title of my talk is focused just on coastal response to Hurricane Sandy, but I think it's important to make sure that we understand the underlying fundamental background information. What do we know about the science and the geology and the longer-term evolution of the Barrier Island system? So I'm going to go through that a little bit and then talk about the response to Sandy, and then linking the two. How did what we knew about the island before Sandy help inform us to help us understand how and why the Barrier Island responded the way it did. And then, of course, to talk a little bit about some of the preliminary findings and what's next. There was money was given by Congress to the Department of Interior last year, and my group was awarded a substantial amount of money to focus at Fire Island, both onshore and offshore. So we will be ramping up some additional research efforts. So I think probably everyone in this room knows, but this is my classic introductory slide. Fire Island is actually the central barrier island in a barrier island chain that extends along the entire south shore of Long Island. It's the longest of those barrier islands, and it's actually, along with Assateague Island in the Delmarva Peninsula, those are the two longest barrier islands on the eastern seaboard. As everyone, again, I'm sure is familiar, the majority of Fire Island is within the majority of the island is within the boundaries of Fire Island National Seashore, and there are also a variety of privately developed communities, a state park and a county park and a federal wilderness area that are all distributed and interspersed along the Barrier Island. Okay. So what's the motivation for the work? What is a geologist from Florida doing studying Fire Island? Well, before I moved to Florida, I was up in the Northeast, and as part of the Northeast region and working with the Park Service, I got involved at Fire Island. The real motivation stemmed from a series of very intense nor'easter extratropical storms that occurred in the early 90s. It really seemed to accelerate erosion issues along the Barrier Island after a long period of quiescence. Probably since the early 60s, there hadn't been a lot of really severe, serious erosion problems. And of course, part of the erosion problem is that the density of the communities begin to increase. So more development, more concern about erosion that may impact that development. So in the 90s, there was this perceived notion that there was a problem with increased erosion. Also, the Army Corps of Engineers has been working for over 40 years to try to develop a sediment management plan for the entire south shore of Long Island, and Fire Island is, of course, within that area. And one of the things, there's beach nourishment, and beach nourishment is part of the sediment management plan, or the proposed sediment management plan. Also, things like filling breaches when they occur, closing them off to make sure that maybe there's not increased flooding along mainland coastlines, and even just things like beach scraping. All these practices are done to mitigate erosion, yet it's really not totally clear what the effects of these practices are on the natural resources. And so that's sort of why we partnered with the Park Service to try to put some science behind some of these issues. So the objectives, you know, what are we doing? What are we trying to know? Well, from a scientific, from a geological standpoint, we ideally want to understand change, beach and dune change, morphology change, on a variety of time scales. Long time scales, a century of change, very like near term. When I talk about near term, I'm talking about years to maybe a decade, and then event-driven change. What happens during Sandy? What happens during a typical nor'easter? We know, and I'm going to show you a little bit today, that there are connections between how the barrier island eroded during Sandy, didn't erode during Sandy, as well as nor'easters, and the underlying configuration, geology, and bathymetry of the seabed just offshore of Fire Island. And then ultimately the goal here is to use this information to develop better models for predicting not just storm, but also sea level rise response, so much longer term impacts to the barrier system. Oops. So the question specifically we're trying to answer, or I'm going to provide some answers to you today, are what do we know about the geology of the barrier system? What have we already established? What are we learning about the subaerial system? So just, the beaches and dunes, the things that are most impacted during storms. What are we learning about how this system has evolved in the past and how it responds to events? And then what is controlling, what sorts of things, that sort of the combination of these two is what's controlling or influencing that response. So the little background information on Fire Island is fairly well established by researchers through the 80s and into the mid-90s. Is what you're looking at here here's Fire Island running along here. So this is what you're looking at here is an image of the intercontinental shelf offshore of Fire Island. The gray and white in the background, I'll show this a little bit better, but that's a side scan sonar image. Essentially, it's just a reflectance off the seabed. And so where it's very bright, that's coarser grained material, and where it's more gray, that's more fine grained material. But so that just helps us look at the distribution of materials. But superimposed on that, what you'll see are these orange and yellow blobs, if you will. And there's lots of material here. What that is sand, and it's thickness of sand. So the brighter the red, the thicker the sand. So as some people may be aware, there are a series of what we call shore-faced attached sand ridges on the western part of Fire Island. So you see these sand ridges, they're long, linear, they're actually attached to the beach system just off in the near shore environment. As we move from east to west along the barrier system, you'll see that on eastern Fire Island, the seabed is largely devoid of those types of sand deposits. There's a little bit here, but it's not really well formed into the same types of ridges that we find on the western side of the island. Other things that I wanted to point out on here, again, if you run along the trace of Fire Island and you're coming right along here, all of a sudden you'll notice this sort of change in orientation in the barrier island itself. And what we have established about how the system has behaved sort of in geologic times over longer time scales is that from right around this point of Watch Hill, right where that kind of crook in the island is, this whole part of the barrier island has been moving landward over many, many years. And some of the just obvious evidence for that is, look how close it is to the mainland as opposed to over here, the distance between the barrier island and the mainland of Long Island. So from Watch Hill to Moriches Inlet, Fire Island has actually been what we call transgressing, moving landward, and it does that through storm processes like Sandy. The area right in here, kind of where these big sand ridges are and this big blob that I'll talk about in another slide or two, this is the oldest segment of the island. That's really been rooted there. It's been sitting there. It's very stable. It's very heavily vegetated in many areas. And then from about Point of Woods all the way to Democrat Point, geologists have established that that whole segment of the island has been prograding west. So the island, many, many years ago, thousands of years ago, used to sit here, and it's been prograding westward ever since. The bottom line here, the take-home message is different parts of the barrier island have in the past and are continuing to evolve in different ways. And having that knowledge helps us understand what happened during Sandy to some degree. This is just another look at a similar data set. In 2011, my colleagues at the Woods Hole USGS went out and collected new state-of-the-art bathymetric and geophysical data of the seabed off of Fire Island. That previous slide, that was from data collected in the 90s, and it was an older technology, and it was very coarse grained, so it was limited in what kind of interpretations you could make of the data. But this is 2011, really beautiful bathymetry. The bluer it is, the deeper. You can see some of these linear features in the inner shelf here. It's kind of covered up largely by this black and white overlay, which are those sand ridges again. So in this image, these sand ridges, this is the thickness where it's black, it's the thickest. So you have this series of sand ridges. And you can also see something. If the lighter white is less sand, less thickness of sand, and the black is much thicker areas of sand, you can see that as we come right along the coastline, there's actually a large variation of sand. There's a lot right here, right up near the shoreline. There's a fair amount here, but then as we move east to that area that's been moving landward for a long, long time, there's not much sand there. So that's something that tells us about the sediment budget. What is the availability of sand to the beach system to continue to feed it and provide nourishment, natural nourishment to it? And finally, on the geologic framework aspect of things, I like to show this. This is the modern, the 2011 side scan sonar image. And again, you may not be familiar, or maybe you are very familiar with this type of data collection, but essentially, just to summarize what we're looking at here, the way it's been processed is where there's darker grays and darker material, that's more fine-grained, material. Where we have these brighter reflectors, that's more coarse, like mainly sand, but different coarsenesses of sand. And you can see those sand ridges. They stand out quite clearly. If you notice this little kind of weird shape in the middle of this sand ridge, and there's another one here, those are the borrow pits from 2003 and 2009 beach nourishment projects that were conducted along this coastline and are still very visible in the data. And this big blob here has now been interpreted by my colleague Bill Schwab as it's a deposit of glacial material. It's a Pleistocene glacial outwash lobe. So when the glaciers were melting, this delta essentially formed. And this material has been eroding as sea levels have rose over the past couple thousand years. And in doing so, are mobilizing material from that kind of soft glacial deposit and providing the source material to maintain those ridges. And that material is then most likely supplied to feed that prograding spit along the western portion of the island. So we understand a lot more about the geology, the sediment budget, and the processes along this coast than we ever had before. On this slide, the one last thing I wanted to show was if we go along this modern bathymetry, and this is kind of important too for the sandy response, this is a profile, so this is along the coast. It's going right along this red line, and it is just the bathymetry. So on this axis, it's depth, right? So we're just going from west to east, looking at right along this line how the bathymetry varies. So kind of as close to the edge of our data shorewards as we can get. And what is really obvious here is on the eastern side of the island, where we don't have a lot of sand and features, it's very deep and relatively flat. There's not a lot of relief. As we come up, we can actually see the topographic expression of that Pleistocene glacial outwash lobe with some, probably these may be sort of old paleo channels or something in them. And then as we head toward the western part of Fire Island, we see expressions of those sand ridges with, and on the order of a meter or two relief in that area. So it's very striking how eastern, central, and western Fire Island, how the bathymetry of the seabed offshore is very, very different along the coast. Beach and dune morphology. The beaches and dunes, as all barrier islands, are very dynamic. I like this illustration because this is not necessarily in the same place, but this just very well demonstrates how beaches can look so different. These are both from Fire Island, and what you can see in this lower one is how undulatory or crenulated the coast was that day. So the beach is going in and out with these big mega beach cusps. And on other days and in other places, the beach is very straight. So it's hard when we're trying to draw a line in the sand and use that to measure how much the beach is changing. There's a lot of variability, and that changes depending on the tides and the wave climate of a particular day. So we have to take that into account when we're analyzing our beach and dune morphology data sets. What we have found in recent studies, this was work done by a graduate student of mine, Erica Lentz, and just to take you through it, really, I'm just going to show you 2 locations. This is the cross-shore profile of the beaches and dunes. So if you were standing on the beach looking down, we just cut it cross-section. So here's the dune going to the beach, the water's over here. This is mean high water. The top plot is 3 dates. We have topography that we generated from 1969 aerial photos. The yellow is 1999, and the blue is 2009, and this is in location B. The top plot is in location B. And what we can see is the idea here is these are comparing the morphology from the eastern side of the island to the western side of the island. So the lower plot is east, so that's located over here. You can see that in 1969, on the eastern side of Fire Island, we have this profile shape. It's been eroding steadily back, but one thing you'll notice is that it's fairly steep. It's fairly high compared to the western profile, and it's been kind of maintaining its same shape through time. This is evidence that the dune and beach system is actually just simply moving back. It's maintaining its volume, but simply shifting back toward, again, moving landward, essentially toward the mainland coast. Whereas on Western Fire Island, we see the beach back in 1969. The dune was back here. It's kind of steep. In 1999, it's much less steep than especially compared to the eastern side of the island. So the point of this is just that from east to west, we see very demonstrable differences in the shape and the elevation of the dunes as well. A little bit about shoreline dynamics. One of the things we focused on is developing these long-term shoreline change data sets, and this one in particular, it goes through Sandy. So this was the data set that was flown, shorelines extracted from LiDAR flown right after Sandy. We've got about 70 shorelines in here to look at the long-term trend. So what you're looking at here is the rate of change. If it's green and above that center line, that's the places where the beach is actually accreted or prograded, moved seaward. If it's below that 0 line in red, that's where it's erosional. And I think the one thing, and this is distance along shore, so it just correlates to distance in the map, but I think one thing that kind of would jump out at anybody was in the eastern side of Fire Island, you have pretty massive, sustained erosion over that 70 to 80 year period. In the center part of the island, over this time period, we are actually, the island is prograding, it's building out. Not huge amounts, this is a meter, so it's not like you would stand there and watch it build. And then on Western Fire Island, now it's erosional in some places and accretional in others, and it just kind of fluctuates through time. So if it's pretty obvious by now, I'm going to skip these 2. It's pretty obvious by now. This is that same plot, right? So here's Central Fire Island with it being accretional or above 0. Here's Eastern Fire Island with the erosion, pretty substantial erosion, and then the highly variable western side of the island. And here's that geology that we looked at earlier. So we see that right where we have that big feature offshore, that Pleistocene glacial outwash lobe, which has its expression here, that corresponds almost exactly to the area where the island is very stable and even over certain time periods prograding. Where the offshore area is deep and flat and devoid of sediment corresponds exactly to where we have that long-term erosional problem, if you want to call erosion a problem. And then I just put up that same bathymetry to demonstrate that there definitely seems to be island response is definitely related to the geology and to the bathymetry of the seabed offshore of Fire Island. Okay, so we were doing all this work. It's really cool. We're understanding a lot more about barrier islands. We're hoping what we do is useful to the Park Service and other land managers and planners. And then Sandy came. So we always had missed storms, because what typically happens with the USGS is when a storm occurs, when a nor'easter occurs, if someone says, hey, there was a lot of erosion or there was a lot of impact, we go collect data after the storm, but we don't have anything right before the storm, so we never know whether the change that we document was from the storm or whether it was from the 6 months, back to our last actual survey. So, being the crazy geologist that I am, when Sandy was approaching the the Long Island coast, Myself and 2 techs actually flew up from Florida to go out onto the beach and survey right before Sandy. With help from the Park Service, we were actually out there while they were evacuating Fire Island. We were out there collecting data on the beach. So we rode the storm out in a Marriott over by the Islip Airport and sat there in the dark for 4 to 5 days. It was a unique experience. We got very tightly bonded with our Park Service colleagues. Okay, Sandy, I think everyone knows, largest storm on record in the Atlantic Basin. Record significant wave heights on the buoy offshore of Fire Island, which is about 27 kilometers offshore. 9.6 meters, definitely the storm of record. But a part of the story of Sandy and impacts to the beach in response to the Barrier Island system wasn't only Sandy, it was the winter following Sandy. Everyone knows it's a very stormy winter. Here what you have is significant wave heights through time. So this is October through May. Here's Sandy at 9.6 meters. But you can see that there were actually 7 nor'easter events that occurred that had significant wave heights of greater than 4 meters that occurred in the months following Sandy. So what we'll see is that you take this system that was hugely impacted, highly deflated, and then you push all these really substantial storms. You know, this was a stormier than normal year, and we look at the impacts of that and the recovery. So here's how we do what we do. It's not really rocket science in terms of the kind of equipment that we need, but you know, with help for certain getting to certain parts of the area, the Park Service actually brought us over by boat, and we used one of the Polarises rigged up with GPS, differential GPS. We either drive along portions of the beach or, where necessary, walk across shore profiles up and over the dunes. And one of the things that we did that was just utterly fantastic, it's going to be for a long time one of the best records of understanding storm impacts and storm changes, is that the Park Service, with a bunch of volunteers in probably a month to 2 month time frame after Sandy, went out and mapped the aerial extent and thickness of every overwash area. So we have a sense of how much material was removed pretty much permanently from the active beach and dune system and is now supplying material to the center part of the island. And that's something we've never had before. So now we're going to look at some of those profiles. So this is BJ walking up over the dune, and this is what the data from that look like. Where we are is here on Western Fire Island. I'm just going to show you 4 of our profiles today. The different colors, I hope you can make some of them out. There's a lot here, but the blue, this is our pre-Sandy, 2 days before Sandy hit. And then I'm tracking through our we're still continuing to monitor the beach, and the most recent survey was September 19th. Actually, my guys were out this week collecting a December survey. But so here's what we have. This is around the area of Fire Island Lighthouse. Here was the profile. The elevation of the dunes was closing in on 5 meters, really big, nice, robust dunes. And the Sandy is the red. So that was 2 days after Hurricane Sandy. The red, it was as soon as we get out there, it may have been 3 days. Here is the profile, you can kind of barely see it, after Sandy. So we lost huge parts of the primary dune system, lost the entire berm. And this plot here is through time, so October through September, and this is the volume change on the profile. So it kind of summarizes how much was missing. This was the pre-storm pre-Sandy volume, and then this was the post, and then this is the profile through the winter through to September. Part of the story, it's not as dramatic here, but so there was our post-Sandy line. The black line is our winter low. So this is what the profile looked like as those storms continued to impact the beach. But finally, if we look at September, we're coming back. That beach, and especially the berm, was really starting to rebuild itself by September. Another profile, just shifting closer to Ocean Beach, so that first one was right here, and now I'm shifting a little bit further west. Again, you see here's the pre-Sandy, the red is post-Sandy. You can see it just was, the whole beach was planed off. This is how much material is missing that I'm outlining here, and that was that drop. Not as substantial as the previous one, but look at the tracking of the volume loss here through the winter. Substantial, it's plummeting. The black line is our winter low. There were many profiles where the majority of the beach was below mean high water by that winter low period. So this was a very, very vulnerable beach system. But here we are again here in September. Look at how much that system has recovered over the winter months on its own. I mean, it's pretty remarkable that material is building back onto the beach that rapidly. All right, profile 23. Now what we're doing, of course, is, as I probably, you could probably tell from my earlier part of my presentation, we really wanted to explore the response in eastern and western Fire Island because we knew geologically those were different. So here we are moving over toward Watch Hill, kind of in the central part of the island. Here are these beautiful dunes at Watch Hill, or near just east of Watch Hill. A little over 7 meters in elevation, and this is how much was lost during Sandy. I think this was the most impacted of our profiles. You can see the volume loss here, and again, changing through time. Here's the post-Sandy. This was very typical of what we saw. Again, the whole beach was just planed off, and in a lot of places, the dunes were just planed down as well. Here's our winter. Actually, here's the brown here is our winter low. Look at how low. This is mean high water. This area was just continued to erode through time. But again, here we are. So a lot of the material that was removed from the beaches and the dunes was carried offshore, just, you know, kind of the near shore bar area, and through the summer it just naturally fed right back on. And last profile I'll show you, this is a little bit further, this is just getting into the very edge of the wilderness area. Here was the pre-Sandy, nice, healthy dune. The dune actually survived here. You can see it in this picture. This was taken right after Sandy. Got a vertical scarp on that high dune, but the dunes weren't destroyed. So you have dune, which now what is starting to happen is we're starting to build the dune back through aeolian processes because there's something there for it to build against. And the beach is building back nicely as well. So it's nice to see that natural recovery. So our profiles were just single locations. So they only tell part of the story, that you can't really look at the spatial distribution, spatial variability. So another metric that we use to assess change is shoreline change. So it's kind of the interface between the wet and dry portion of the beach from the last incursion of high tide. So what you're looking at here is distance along shore. So this is just the map where we are. And this is net shoreline movement. And again, if it's up here, it's accretional, it's actually building out, progradational, or if it's below the line, it's erosional. So the blue line kind of stuck in the back here, that's our pre and post Sandy. So this is from October 28th to November 5th. Look at the shoreline. It gained in every place. If you were just measuring the shoreline, you would say Hurricane Sandy caused the beach to accrete, to gain. Well, we all know that isn't true, but what happened, well, it is technically true, but what happened is so much material was pulled from the upper part of the beaches and dunes and was deposited on the lower part of the beach that this is what we recorded. The beach was lowered. The elevation was substantially lost, but the actual shoreline that we measured actually during the storm or as a result of the storm accreted. But then look what happens during the winter months. So from post-Sandy to March, the shoreline is just massively and substantially erosional. And that really tells more of the picture. You had this very deflated, flat, vulnerable beach and then got hit by these series of nor'easter storms. And this is what it left in March. But between March and just this past September 13th, this has been the recovery. So that shoreline is basically back to where it was post-Sandy. And that's a good indication that there's enough in the system that it's coming back. That doesn't mean to say there's not problems out there, but there is indication that there's natural recovery going on. And the bottom plot is just, it sums it up. So this was October, so pre-Sandy to our most recent survey. So this is the total change, Sandy, nor'easters, all the data. And you can see that overall, there's areas of erosion and areas of accretion, but if you probably added all this up, you wouldn't have a lot of net change. So for the shoreline, Sandy doesn't really seem to be a big part of the story. What is a big part of the story is the overwash deposits. And I'm going to walk you through some of the results. This was such a nice collaboration between Park Service staff and volunteers and the USGS. we kind of devised a protocol for getting out and collecting collecting the deposits. And one of the things that was so critical is we knew that if we wanted to document the thickness of the deposits and the extent of the deposits, we had to get out there before people, especially in the community, started bulldozing that stuff out of the streets, from underneath their houses, pushing it back down onto the beach, and we would never really have a record of what the distribution of the overwash from Sandy was. So like rock stars, the Park Service went out, I forget what the number is, but it's something like 759 data point locations they collected over a period of, what, a month and a half, 2 months. Amazing, amazing data set. We supplemented the field collected data with aerial photography, helping to outline the area, and then we used techniques in ArcGIS to grid using both LiDAR data and the field data to create thickness maps where we could then estimate volume. So the question we're asking is, what was the volume of material that was removed from the beaches and dunes that was deposited in the interior portion of Fire Island? One of the things we noted, and I'll show you the volume results on the next slide, is that the characteristics of the overwash deposits definitely varied from eastern to western Fire Island and central Fire Island. So on the western portion of the island, where there wasn't a lot of development, you just had these really thick sheets. It was almost overwash sheets. Whereas your more classic overwash are these fans or tongues in the case of the area around the still open breach, where it just punches through dunes but leaves the dunes remaining and then deposits these splay fans out back behind the primary dune. Whereas on Western Fire Island, it's just kind of like a wall. All the dunes were completely wiped out and all that material was carried landward. And then in the communities, obviously, the translation of sediment from the dunes and the beach was impeded by the structures there, so it can only make it so far inland. So here is 3 maps. We have the information for the entire island, but I'm just showing 3 locations around Fire Island Lighthouse, over near Watch Hill, and then over in the area on eastern Fire Island. What you're looking at here is, this is A, so this is the area around the lighthouse. There's a parking lot at Robert Moses. But this is sort of, you can see that kind of characteristic. It's just a big overwash sheet of the overwash deposits, thicker in some areas, not as thick in others. Here's the scale there where it's darker. You had thicker deposits. In the communities, it just kind of utilized existing lows, walkways, existing breaks in the dune, that sort of thing. In B around Watch Hill, again, the dunes are largely maintained in this whole portion of the island, and there were probably lows in the dunes that the storm took advantage of and surged and broke through those, but there were remnant dunes, eroded, but remnant dunes in between the overwash deposits. And then finally, on eastern Fire Island, it was just free for all. I mean, the dunes were wiped out. It was, transport from ocean to bay in many, many places along the island. But what is really interesting is when we look at our volumetric calculations of the overwash deposits, all told, if we measured how much the dunes and the beach lost, and then we compared that to how much was deposited in the overwash deposit, and it was only 14%. So of all the sand that was lost from the beaches and dunes during Sandy, only 14% ended up on the interior portion of the island. The rest was carried offshore. Some of it's coming back on. Some of it was probably carried maybe too far offshore to be recoverable, or was carried down coast. We don't know the answer to that yet. But if we look at if we divide the west, central, and eastern portions of the barrier island, so west is roughly to here, central and eastern, look at the differences in the overwash volumes. So where the center part of the island, where we knew before the storm that the island, and especially the bathymetry of the inner shelf offshore, was higher, there's more sand there, and there's probably protection from waves, we had a lot less overwash and overwash volume as compared to the west and east, which weren't really that different. If you're interested, all this has been summarized and is available in a USGS open file report that was published in August, so that's online if this is of interest to anyone here. Just wanted to make a point of mentioning that is available. We are working toward a few other efforts, and one of the things we're going to focus, I'm not going to talk much about the breach because the next speaker is going to give you all the details on that, but we we realized one of the problems, or one of the problems that we wanted to address scientifically, a scientific problem, is trying to understand the morphodynamics of the breach. So the big question is, will it close on its own? Won't it close on its own? How long is it going to stay open? Those are very complicated questions to answer, but very valuable if you can start to get at the answers to them. But we were, there's a possibility that the breach might be mechanically closed by the Army Corps. There's the possibility it would have closed on itself, on its own over the summer. And so one of the things that we wanted to do is at least get one really good, tight survey of the entire breach system, not just the channel, but also the deposit of sand in just offshore and a little bit of the coast up and down. Offshore deposits. This is a very hard place to work because this is where the waves are breaking. So we actually brought this amphibious vehicle up from, actually it was an Army Corps of Engineers research facility in Duck, North Carolina. They transported, this thing can drive off the beach into the water. And so we were able to get bathymetry all the way extending to about 8 or 9 meters water depth, and that's going to be really valuable. Our plan is to put these into morphodynamic models that can actually predict the evolution, not just of this breach, but breaches along this portion of the coast in general. So we're excited. We haven't started working with it. That's part of our Sandy supplemental research, but we did collect this one data set this summer. So just going to kind of start summarizing some key points. What is it that controlled or influenced the response of the barrier system to Hurricane Sandy? Well, I think it became obvious as we thought about it and looked at our previous data. Pre-storm elevation of the dunes is huge. Pre-storm height and slope of the beach, kind of as I showed you in those long-term profiles that we had going back to 1969. Pre-storm volume of sand in the beach. How much sand is available for the system to recover? Something that's of interest that a colleague is exploring right now is how much did the different shapes of the sandbar offshore influence the wave energy reaching the coast? And it turns out this could be a substantial piece of how Fire Island responds during a storm. And finally, the variations in wave energy reaching the coast. That's kind of like the take home. We know that. And so I'm going to do conclusions, and then if I have a minute or two, I'm just going to talk about some of the things that we have coming up. But so here's essentially what we found primarily from our research on Hurricane Sandy was that, kind of surprisingly, but when you think about it, not really at all, that the shoreline grew seaward as a result of Sandy. So if you were studying Fire Island 50 years in the future and all you had to look at was the shoreline, it would tell you a different story than what we knew actually happened out there. So it's just kind of a cautionary thing. The beaches, so that means that the beaches were widened from Sandy, but we lost a lot of material from the upper beach and dune, thus making really the system more vulnerable to future storms. The dunes were overwashed on our calculations along with just under 50% of the island, and the volume loss was nearly 50% of the pre-storm volume. So of the volume of material in the dunes, that's a lot of material that's now either on the beach or in the surf zone or back in the center part of the island that may or may not be available for aeolian recovery of the dune system, or it's going to take a while for those to really build up on their own. We did note, obviously, that the dunes and the beaches continue to erode substantially through the winter, and in many places the elevation lowered below mean sea level. But that summer recovery was actually stunning to us. It was really nice to see that the system was still working, was still functioning even after Sandy. The response of the coastline really was not unexpected, not both spatially and temporally. The variation, we can pretty much say the variation is really related to the antecedent geology, which we had already demonstrated controls the variations in the island morphology, sediment availability, and wave energy reaching the coastline. So what's next on our map? As I kind of got at, we're very interested. This is a picture, it's kind of hard to follow. This is Fire Island turned on its head now. We've been surveying a 30-kilometer long stretch of coast that does capture some of eastern, central, and western Fire Island. What you're looking at here is actually, this is the outer bar. So this is offshore, this is the beach. And this was taken using a really high-tech instrumentation. It's radar, and the radar bounces off the waves breaking, and we can back out bathymetry. But one of the things that we noticed from this is this offshore bar really varies along coast, and we want to correlate the variation in the offshore bar with what kind of changes we see on the beach during a storm. Part of that work is going to be done. We're also going to collect bathymetry of the whole system. That work's going to be done. We're going to bring this amphibious vehicle back up in late May or early June of next year and collect a bunch of bathymetric and geophysical data in the nearshore environment. And also, almost as we speak, the USGS has contributed in cooperation with the Army Corps of Engineers, and we're remapping the intercontinental shelf off the coast. Part of this effort will allow us to see how much Sandy moved all those sand ridges and the sand resources offshore. It's really critical for a lot of understanding of recovery and availability of material for nourishment efforts and that sort of thing. And we're also working on actively developing some wave models so that we can simulate storms as they're approaching and try to predict how the system might respond to those storms. And so I don't know if do I still have a minute or third? Yeah, so this is just some considerations that have been occurring to me. I did a detail helping FEMA out as a coastal science expert in last winter. And was really involved in some of the recovery activities. And I think that one thing that we need to make sure we do with this storm and even storms in the future is this concept of taking what we know about the science of the system and understanding that there's a geologic influence on the resiliency of a system, and it varies from place to place. If you rebuild the dunes along Fire Island identically from east to west, same slope, same height, from east to west, I can guarantee you they're going to behave differently over the course of the next 2 years, 5 years, decade. So maybe we need to start taking into account a little bit about what we know about the geology and the evolution of a system as we approach coastal restoration. So that's my soapbox. Thank you.
The information you have provided on the offshore sand ridges and the barren area to the east certainly would be of great interest to fishermen and who are trying to catch things. I think the next thing to do is to look at those ridges in the eastern end and see what the difference in the fisheries are.
I think that's an excellent approach, and the USGS would welcome collaboration with biologists and ecologists. I know nothing about fish or habitats, so happy to do that.
Hi, Cheryl. How are you?
Good.
Just a quick question. When you were doing the shoreline change and you had showed the recovery after Sandy, was that mean high water, mean low water? When were those?
So the surveys are mean high water contour. What we did instead of wet dry line. So what we did when we did our surveys, we ran a line on the upper part of the berm and then as low on the beach as we could, and we interpolated then the mean high water contour from those field data. So they're comparable to LIDAR, so we can use LIDAR data in comparison with them. So it's a mean high water contour.
Okay.
It was a great talk.
Thank you.
Will those overwash deposits on the bay side eventually get vegetated? Are they permanent features?
To some degree, absolutely. So, I mean, if you think of, a map of Fire Island, and you think on the eastern part of the island, there's a lot of marsh deposits. It's very crenulated on the backside of the island, especially eastern Fire Island. Those are all old overwash deposits that have been vegetated. So certainly the overwash that reaches the bay provides substrate for marsh development.
A lot of the towns on the next island over on the west do Christmas tree planting. Does that do anything?
I think they don't plant Christmas trees, right? They put their Christmas trees on the dune, right? The Christmas trees function to capture aeolian, wind-blown sand. So, to each his own. If you don't mind the way dead Christmas trees look along the base of your dune, sure, it'll help capture sand. So there's really nothing wrong with that as kind of a erosion mitigation that's very nature-based, is the common terminology.